So now you can see the final chart, the final visual, and this is the QC chart, or the change chart as I like to call it. The QC chart has the measured mean at the center, the current mean, and uses the current SD limits to set the plus and minus 2 SD that are shown here at the red lines. This is what you expect. After this blue line, I've simulated a shift to unacceptable risk. After the blue line, one of the 20 results afterwards exceeds the allowable error limit. That means 5% of the results are clinically unacceptable. What we're seeing on this QC chart is exactly what people think they always see, that shift in the mean would be noticed immediately. But watch what happens as the gap between where you are now and where you would be if the method failed becomes smaller. Let me shift that up to 104. Now the sigma is 6, the margin for error is 4. We have a wider spread to the data. Let me shift it now up to 105. Now you're seeing that of the 20 points afterwards on the QC chart, there's one that's not flagged, but still 19 are. You'd probably see that in the first run. What if I have a mean of 106? Well, that's a different situation. Now, only 50% of the results afterward are flagged. That's because the margin for error is 2 SD. If it shifted 2 standard deviations, the method would fail. An unacceptable risk level would exist. If it shifts 2 standard deviations, you know this from the statistics, if the new mean is 2 SDs higher, 50% of the results are above the mean, 50% are below. There's only a 50% chance you're going to detect that error. So although the risk is acceptable now, this QC process is not effective to detect this shift in the mean. And if my current mean drifts up again to 107, you can see that this method can only shift 1 standard deviation before risk is unacceptable. There are only 4 out of 20 points flagged after that shift. The odds of detecting this shift in the first run are about 25%. This is a 3 sigma method. Now let's go back with this in mind when you can see the relationship between where you are now and the probability that you're going to detect unacceptable risk if that risk occurs, depending on the current mean, the current SD, and that determines the margin for error. The margin for error determines the probability that you're going to detect simulated clinical shift in the first run. These numbers really do matter. The question becomes, what is the acceptable risk? Risk management is black and white. It's a simple matter of comparing the estimated risk to the given risk criteria to determine the acceptability of the risk. That's exactly what the simulator is doing. What is an acceptable risk level? Well, current risk is driven by the analytical process quality and apparently the quality management process. Glucose. How many methods could achieve a 0.1% risk level? In the group from 2012 to 2014, only 1 of 34 QC samples had a risk above 0.1%, and it was 0.12. In the year 2000, when they did not use QC software, 25% of the samples had risk above 0.1%, and the highest risk level was almost 6%. But back in the year 2000, when they used QC software to every month manage that question of where am I relative to where I want to be, they were as good back then as these labs are now. Isn't that interesting? Can you use an acceptable limit of 0.1% for glucose? Quite possibly. And if we can, why not? But for sodium, don't try that. It simply doesn't exist. If the allowable error limit we're using, the 4.0 based on CLIA, if that is the right limit, then 34, 46, 20, and look at that, only 20% of the methods back in the year 2000, 20% of 51 QC samples then were unable to meet this standard. 35% are now. That's what happens when you manage quality regularly, saying, is this where it should be? I had not looked at that data before. That's why I sound so surprised.